Good afternoon, sir.
Good afternoon. Okay, shall we begin? हेलो
सर अभी 4 स्टूडेंट ज्वाइन हुए हैं।
हाँ, तो हम रिकॉल कर लेते तब तक कुछ जो चीजें लास्ट टाइम कर रहे थे।
ओके
आप मुझे
यस सर।
कहाँ पर रोका था बताएंगे? तो
सर लीनियर स्पैम वाला बताया था आपने, एलएस और एलएस डैश में डिफरेंस इक्वल होंगे कि नहीं होंगे, ये वाला क्वेश्चन।
ओके, गुड। So is my screen visible to everyone? Hello?
जी सर।
Okay, let's start.
Yes, sir.
So last time what we were doing,
यस सर।
we first define linear combination.
यस सर।
Then we saw linear span. Okay, linear span of a set S. Let us recall what was the linear span of a set. So suppose we are given a set S in a vector space V, non-empty set. Then by LS we defined LS like this: to all finite linear combination A alpha I Si, where this K is a positive integer and alpha I belongs to the field and Si this belongs to S. Okay, this is how we find LS, correct? Then we have another name for this LS, we call it span of S, or set generated by S, or set spanned by S. Then there was a question. What was the question? Question was, we have two sets S dash and S of a vector space V, where S dash is a subset of S. And the question was whether LS dash equal to LS or not. Is the question. Okay. Whether this is true or not. So, how did we answer this? We answered, we took so we took a particular set S dash and we took S like V comma W. We said that LS dash equal to S if W equal to alpha V. Correct? So from here, then we ask another question. So say if we have we accept VW, which is our S dash, then S is UVW, then LS dash.
सर स्क्रीन पर कुछ show नहीं,
हाँ बोलिए।
सर स्क्रीन पर कुछ शो नहीं हो रहा है, मुझको नहीं हो रहा, बाकी को हो रहा है,
सर
तो शायद
दिख रहा है,
हो सकता है
सर
मैं
हो रहा
मुझको।
है।
सर
अनुराग
स्क्रीन
दिख रहा
शो
है,
हो रही है और रन भी कर रहा है।
अनुराग ये दिख रहा है क्योंकि मैंने 2 सिस्टम में लगाया हुआ है अपना वेबएक्स, तो मैं चेक कर रहा हूँ कब रुकेगा कब नहीं रुकेगा। अगर आपको नहीं दिखाई दे रहा तो आप सुनिए, अपने नोट्स को देखिए। मैं ये रिकॉर्डेड लेक्चर में अपलोड कर दूंगा तो आप बाद में देख सकते हैं।
सर ये कौन सा लेक्चर आप पढ़ा, लेक्चर 5 है लेक्चर 6 है?
मेरे पे भी शो नहीं कर रहा सर।
सर स्क्रीन की आपकी स्क्रीन शो हो रही है, लेकिन स्क्रीन पे जो आप बोल रहे हैं जैसे पहले टाइप करते थे वो सब पूरा शो होता था, रिटन फॉर्म में वो नहीं शो हो पा रहा है। बाकी किसी को हो रहा है तो सर ये मेरे साथ ही हो
यस
सकता
सर,
है।
नहीं शो हो रहा है।
कुछ लोगों को नहीं शो होगा, उसका कारण ये है कि उनका नेटवर्क इशू है। ठीक है, तो आप लोग सुनिए, आपके लेक्चर्स आपके पास है, मैंने फाइल आपको सेंड की हुई है। ठीक है, आपके पास।
सर ये लेक्चर कौन सा आपका है, ये 5th वाला है, कंटिन्यू कर रहे हैं कि 6th वाला है?
अभी रिकॉल कर रहा हूँ लास्ट टाइम का, मैंने एक कल जो भेजा था उसमें ये सब लिखा हुआ है पहले से, 4th 5th वो एक ही आपको देखेंगे तो एक ही
यस
नोट्स है।
सर।
ठीक है, आप ऐसा क्वेश्चन मत पूछिए कि 4th क्लास का है 5th का है या कि कल जो मैंने भेजा उसमें सब 4th लेक्चर 5th लेक्चर 6th लेक्चर एक पीडीएफ फाइल में है। आप देखते हैं या नहीं देखते हैं?
सर देखते हैं।
हाँ, तो आपको ये क्वेश्चन सेम पीडीएफ
सर मुझे
फाइल,
ढूंढना पड़ रहा है ना कॉपी में।
तो आपको ये देखना चाहिए ना। देखिए ये आपको मालूम होना चाहिए, जब आप अगर आपने लिखा है तो कहाँ पर लिखा है आपको पता होना चाहिए ना। ये मैं रिकॉल करवा रहा हूँ लास्ट लेक्चर का, और ये अगर नहीं दिखाई दे रहा है तो आप वेट करिए, वो आएगा आपके में, क्योंकि आपका नेटवर्क थोड़ा स्लो है। और मैं इसके बाद एक रिकॉर्डेड वीडियो अपलोड कर देता हूँ हर बार फोल्डर में, जो आप लोग एक्सेस कर सकते हैं बाद में। ठीक है,
ओके सर।
क्या ये सभी के साथ प्रॉब्लम है?
नो सर दिख रहा है।
दिख रहा है, बाकी लोगों को दिख रहा है अनुराग। ठीक है, अगर वो नहीं दिखेगा तो
हमारे
मुझे
में
भी पता।
सर,
देखिए,
हमारे में भी सर ये प्रॉब्लम है।
अगर वो आपके में प्रॉब्लम नहीं है, वो आपका कोई प्रॉब्लम नहीं है, आपके नेटवर्क का प्रॉब्लम है। इसका कारण ये है कि आप लोगों ने मॉर्निंग से 2-3 लेक्चर अटेंड किए तो डाटा खत्म होने लगता है। ठीक है,
यस सर।
तो हाँ, इसकी चिंता मत करिए, मैं अपलोड करूंगा। ये रिकॉर्ड हो रहा है और ये अपलोड करूंगा आपको। अगर ये नहीं दिखाई देगा तो मुझे पता चल जाएगा कि ये गड़बड़ हो रहा है। ठीक है, क्योंकि मेरे सामने में एक और स्क्रीन है जहां पर मैं देख पा रहा हूँ कि जो भी मैं लिख रहा हूँ वो मेरे दूसरी स्क्रीन पर दिखाई दे रहा है। ठीक है, तो आप लोग चिंता मत करिए, ये रिकॉर्डेड लेक्चर आपको मिलेगा। ओके, और जिनको नहीं दिखाई दे रहा वो अपने नोट्स खोलिए और वहां पर चेक कर सकते हैं। करेक्ट? एनी प्रॉब्लम नाउ? एनी अदर इश्यू? If not, then I proceed. Okay. So what I said is, so if we take S dash equal to VW and S is UVW, clearly S dash is a subset of S. And let's see when S dash equal to LS. So LS dash equal to LS, and we answered it. This is true. This shows when W equal to W is a linear combination of U and V. Alpha U plus beta V. Okay, alpha beta belongs to okay. This suggests definition, which is called linear dependence. So here we call, in first example, we call W is dependent on V. W is linearly dependent on V. In second example, we say W is linearly dependent on U and V. So thus we have the following definition. So we have a vector V in V, and we have a subset V1, V2, Vn, V. We say that V is linearly dependent on V2, Vn if there exists alpha 1, alpha 2, alpha n. In the field there exists scalars such that V equal to alpha 1 V1 to alpha n Vn. Okay, so in other words, this means V is a linear combination of Vi's. V1, V2, Vn. Okay. So now from this we have another definition. So here we said that a vector V is linearly dependent on other vectors. So now we define a set is linearly dependent. When a set is linearly dependent, suppose we have a set S, say S is V1, V2, Vk, the subset of a vector space V, we say S is linearly dependent if there exist scalars alpha 1, alpha 2 and alpha n, okay, such that at least one alpha I is non-zero. Okay, wait a minute. Let me fix the problem. Okay, am I audible?
Yes.
Hello, please.
Yes, sir.
Okay. Is my voice clear?
Yes,
Yes,
sir.
sir. Loud and clear.
Okay. Okay. So yeah, where were I? Okay, we say that S is linearly dependent if we have n scalar such that at least one of them is non-zero. Okay, and this whole alpha 1 V1 plus alpha 2 V2 alpha and V. Oh, it was K. Alpha K Vk 0. So from this definition and from the above definition, you may observe that if we rewrite this equation, this can be rewritten this form: alpha 1 V1 alpha 2 V2 plus alpha n Vn plus minus 1 V equal to 0. Okay, is it true? So this means, so we do not know about these alpha whether they are 0 or not, but surely we know that this minus 1 is non-zero. This means if V can be written as a linear combination of V1, V2, Vn, then the set V, V1, V2, Vn is linearly dependent. Okay. Correct? So let's see how do they look like. What is the geometric meaning of linearly dependent set? Okay, for this, let's consider first consider. So we start from R. Let us start from R over R is a vector space. R is a vector space. So take a non-zero element. So you all know that in a set, if there is a zero element, okay. So I have not yet give you this observation. Observe that if a set contains zero, then it is automatically linearly dependent. Do you see why? Okay, this means say what I'm saying is 0, V1, V2. If this is a subset of V, then it is linearly dependent. Do you see why? Because there exists alpha 1, alpha 2, alpha 3 in R, okay, in K, take alpha 2 equal to alpha 3 equal to 0 and take alpha 1 non-zero. You may take any alpha 1. So whenever you multiply 0 by alpha 1, it will be 0. And now you are multiplying by V1, 0 by V2 by 0 and V1 by 0, you will get 0. Okay, so here this alpha 1 is non-zero, therefore this set is linearly dependent. Okay, so now another example. So say we are in R and take a set 1, 2, or so this is a particular, take general set, take alpha 1, alpha 2, where alpha I, these are non-zero real number. Yes? Suresh.
सो नहीं हो रहा सर, कुछ आवाज क्लियर आ रही है बस।
सुरेश आपको आपका नेटवर्क स्लो है, इसलिए आपको नहीं दिखाई दे रहा है। ये रिकॉर्डेड लेक्चर आपको मिलेगा, चिंता मत करिए, ठीक है सुरेश?
यस सर,
सुन रहे हैं? हाँ, ये क्योंकि देखिए ये कहीं भी प्रॉब्लम आ सकती है। इसका कारण है कि आप नेटवर्क हर जगह सेम नहीं होता, ठीक है, बहुत बार स्लो हो जाता। क्या ये सबके साथ दिक्कत है? यहाँ पर कुछ लोग तो ऐसे होंगे जिनके साथ ये दिक्कत नहीं होगी।
Yes, sir, I am also facing the same problem.
You are also facing
सर गूगल मीट ही join कर।
Sir, I'm not facing the problem.
See, the problem with Google Meet, if you face the same problem, you will not get any recorded lecture. So here you will get a recorded lecture.
Sir, please don't go for Google Meet, sir. Sir, please don't go for Google Meet, sir. It is best.
See, I can go with Google Meet, but problem is that if you not see, if it is not accessible to you, then you will not get any recorded thing. Okay, recorded lecture. Here, if you miss something, later you will get. Okay.
Yes. Don't go for
Hello?
Google Meet, sir. Webex is.
Who is this?
बट सर अनुराग भारती।
अनुराग बोलिए।
सर आज बस इश्यू ये हो रहा है कि सर आपकी वॉइस एकदम पूरी क्लियर आ रही, बट जैसे स्क्रीन पहले मूव होती थी, स्क्रीन पे पूरा टाइप हो रहा था, वो से अब आज नहीं हो पा रहा। बस बाकी इश्यू कोई नहीं आज।
अनुराग, मैं आपको फिर से बोल रहा हूँ, ये प्रॉब्लम गूगल मीट में भी आ सकती है, ये यहाँ भी आती है, ठीक है, ये कहीं भी आ सकती है।
सर मैं
गूगल मीट
गूगल
में
मीट
अगर
के
ये,
लिए बोलता ही नहीं हूँ, सर मैं गूगल मीट के लिए बोलता ही नहीं हूँ, मैं इसीलिए ही बोल रहा हूँ कि आप वेबएक्स पे ही कंटिन्यू करिए।
हाँ तो मैं यही कह रहा हूँ ना, देखो ये प्रॉब्लम आ रही है, इसको थोड़ी देर आप फेस कर सकते हैं। आप सुन तो रहे हैं ना मुझे, आपके पास आपके
यस
नोट्स
सर,
हैं,
यस सर,
आपके समझ, अगर जो नहीं आ रहा है बाई चांस, वो आप बाद में रिकॉर्डेड लेक्चर में सुन सकते हैं,
यस सर,
देख सकते हैं वहां पर। ठीक है, ये बात समझिए आप।
यस सर, कंटिन्यू सर, सॉरी फॉर डिस्टर्बिंग यू।
ठीक है, ओके। So where were I? Okay, I was in vector space R. R is a vector space over itself. So take any two non-zero vector in R. If you take any vector which is zero, then it is linearly dependent. We have seen it. So take any two vectors. Say first tackle this. So you know one can be written as 1/2 into 2. Clear? So this means this set is, and you know 1/2 is a non-zero real number. This means 1/2 is clearly dependent. Okay. Similarly, alpha 1, alpha 2, both are non-zero real numbers. So consider this. So take alpha 2, you can write alpha 2 in terms of alpha 1. So like this. So here, since alpha 1 is non-zero, so this is well defined scalar, it belongs to R, and since alpha 2 is non-zero, this is non-zero. So hence implies alpha 1. Okay. So this implies alpha 1, alpha 2 linearly dependent. Okay. Suppose we are in R2 and we have two vectors v1, v2, v comma w in R2, and they are linearly dependent. How do they look like? So they are linearly dependent, and I'm taking v and w both non-zero. Okay. So if they are linearly dependent, one of them can be written as a linear combination of other. So w equal to alpha v. So, but you know what is alpha v? Alpha belongs to R. So this means this W lies in the line passing through origin and V. So this is our R2. Say this is V. This point is V. Then this W is lying somewhere in this line. Okay. So this is V, and say this is W. Okay. So similarly, if you are in R3 and you have V, W, U, W, this is linearly dependent, then you have two cases. Either W equal to alpha U plus beta V. Okay, you have this kind of cases. So number one, V equal to say alpha U, and W equal to W equal to say beta U plus gamma V, but V is alpha U. So from here, this is W plus gamma alpha U, which is beta plus alpha gamma U. So this means W is some, say this is A dot U. Okay. So this means in this case, if this is the situation, in this case, suppose this is U. In this case, V and W both lie in this line. Okay. In this case, say this is V, and say here this is W. So if this is the case, then U, V, W will lie on on same line that passes through the origin and any point U, okay, or V. Okay, there is another situation where you cannot write V as you cannot write V as alpha U as for any alpha in K. We are taking R. So for any alpha in R, you cannot write V in this form, but you can write W in this form. Okay, this means when we are in this case, then W. Okay, so first recall something. So first recall something. So you know there is beta V plus gamma U. If we vary beta and gamma over R, okay, then this set gamma belongs to R. This set represents a plane R2. Okay, and we write it as L of U V. Correct? This means this can imply from here we observe that W lies in the plane passing through the origin and V comma W, sorry, V comma U, plane passing through origin and U comma V. Correct? So this was the geometric meaning of really dependent set. So, okay, let me give you one more definition, then I'll add. Let's now define sum of two sets. Okay, sum of two sets. So you all know this. You all know what does it mean by sum of two sets. So say we have a set A and in X and B a set in X, then A plus B is nothing but this set A plus B where A comes from A and B comes from B. Okay, so so this is a simple definition of sum of two sets. But why are we interested in this here? So we are interested in this because if you see above in the definition of linear combination, okay. So if you see this sum here, So this is alpha 1v1 plus alpha 2v2 alpha k vk. So this if alpha 1 varies, so alpha 1 v1 is nothing but the subspace spanned by v1. Alpha 2 v2 will give the subspace spanned by v2. Similarly, alpha k vk gives the subspace spanned by vk. And these are so this sum is nothing but sum of subspaces spanned by v1, v2, vk. Therefore, we are interested in the sum of two sets and in particular sum of two subspaces. Correct? And so from the above discussion, you now convince yourself, you may convince yourself that if we have say n subspaces w1, w2, wn, these are n subspaces of a vector space V, then their sum w, which is w1 plus w2 plus wn, is again a subspace. Again, a subspace of V. Okay, and W contains each of them, each of the subspaces, each of WH. Okay. So what does this mean? So recall previous definitions where we said that a subspace S, sorry, a subspace spanned by S is the smallest subspace uh, that contains S. We call that subspace spanned by S or subspace generated by S. Okay. Here also you may prove it easily that W is a subspace generated by W1, W2, Wn, or subspace spanned by W1, W2, Wn. Okay. Any doubt so far? Any question? Hello? Am I audible to everyone?
Yes, sir.
Okay. Any question? Okay. If not, so I'll proceed ahead and let's take a question here. Okay. We were talking about linear dependence. So here is a question which says that if P and W are linear, is this correct? Okay, first I'll define another notion, then I'll come to this question. Okay. So we were talking about linear dependence. There is a notion which is called linearly independent set. Linearly dependent set. So you may guess what would be the definition. So a set S is linearly dependent if it is not linearly. So a set S is linearly independent. I said independent if it is not linearly dependent. Okay. Set S of a vector space V is linearly independent. So be little careful here. See, I did a mistake. It is correct. If S is not linearly dependent. So what does this mean? This means there does not exist any alpha 1, okay, any alpha 1, any set alpha 1, alpha 2, alpha, let me write it again. So say S equal to V1, V2, Vk, not dependent, means there does not exist alpha 1, alpha 2, alpha k, which is never 0. Okay? Such that alpha 1 V1 plus alpha 2 V2 plus alpha k Vk is 0. In other words, if you have alpha 1 V1 plus alpha 2 V2 plus alpha k Vk equal to 0, this will imply alpha 1 equal to alpha 2 equal to alpha. Means all alpha is 0. So this is the definition of linearly independent set. So here is the exercise for you. So if we have set in R2, A, B, and C, D in R2, it's linearly independent if and only if B minus BC is non-zero. Okay, prove it. And see, there is a very nice relation between, we will see this later, but let me bring it out here. There is a nice relationship between linearly independent set and this. If you recall what is this AD minus BC, if you observe, this is nothing but the determinant of this matrix A, B, C, D. Or, let me write it in this way. So this is the matrix. This is the column vector AB, and this is column vector CD. So if you see, if determinant of this matrix is how to do that determinant. Okay, so so it is a small exercise for you. Let me do another simple exercise. Okay, exercise. So if you have two vectors B comma W, B and W be vectors in any vector space, if this is linearly dependent, then V plus W, V minus W is also linearly dependent. And so it's okay. So what does this say? So let us the geometric meaning of this. Okay. We are in, say we are in R2 and we have two vectors, two vectors. So V1 and V2. Then you know from parallelogram, so you know sum of how do you get sum of two vectors? So you use this parallelogram technique. You make a parallelogram. I am assuming that it is a parallelogram. Okay. I don't know whether it is. So okay. Then what would be the sum? Sum is this vector, correct? And what would be the V minus W? This, okay? If this says that if you have two vectors which are linearly independent, then these vectors, this is V plus W and what is minus W. These are linearly independent. And to see this, it is what we do, we consider this definition. This so in computational thing, we will use this definition. What we do, we take a linear combination of vectors and we will show that the scalars alpha 1, alpha 2, alpha k are 0. Let's do the same here. So we want to show that V plus W and V minus W is linearly independent. Therefore, take a linear combination of these two and make it 0. Then by simple Subhas. Hello, Subhas. Please mute yourself. Subhas, mute yourself. Subhas, are you listening to me?
Yes sir, ये म्यूट ही नहीं हो रहा.
म्यूट नहीं हो रहा. आपकी आवाज, आपके पीछे बैकग्राउंड की आवाज आ रही है, वो डिस्टर्ब करती है. Okay, so from a GMs of vector space, this will be alpha u plus alpha w plus beta v minus beta w equal to 0. Okay, take these two plus beta v plus alpha minus beta v equal to 0. But you know it is given that VW is linearly independent. So VW is linearly independent. So whatever linear combination you take, their coefficient will be 0. So this implies alpha plus beta equal to 0. And same thing with alpha minus beta. Since V comma W is linearly independent. Correct? But this gives alpha equal to 0 and beta equal to 0. And we are done. This implies V plus W and V minus W, they are linearly independent. Okay. Next theorem. See a theorem here. So suppose we have V1, V2, Vn subset in vector space V is linearly independent. independent. It is linearly independent if and only if okay, so I did the mistake, sorry. So the theorem says V1, V2, V is linearly dependent. We have already seen if and only if one of Vi is one of the Vi is the linear combinations of the other VIs, other V's, okay? So it is easy to see. So I'm leaving it for you. Now, from this discussion, whatever we have discussed so far, we give a definition of this. Okay. So I said E1 into En of a vector space V is said to be a basis V if every vector can be represented as a linear combinations of these E1 into En, and this representation is unique. Okay. If vector V can be expressed uniquely. So this is very important. This uniquely is very important. Okay. We will see why uniquely is equal to summation I equal to 1 to n alpha I E I, where this alpha I comes from the field K. What does this mean? Uniquely means from uniquely means if we have two such representations, if we have two representations V, that is V equal to summation I equal to n alpha I V E I, and j equal to n beta j E j, then alpha I equal to beta. Okay, so let me write it. Equal to 1 to 1. Alpha I equal to beta I for all I n. Okay, this is the meaning of uniqueness. Correct? So from the discussion that we had in the last lecture and today's lecture, so we discussed two notions. If you remember, we discussed span of a set, and another discussion is about linearly dependent set and linearly independent set. So from this discussion, you may observe that there is an equivalent definition of basis. What is that? Equivalently, E1, E2, N is a basis of V if number first E1, E2, En is linearly independent, and number two, span of E1, E2, En is V. Okay. So it is an easy exercise to see that both the definitions are equivalent. So I said equivalently means these two definitions are equivalent. So the two are equivalent means you can go from here to here and you may go from here to here. So both are equal. Okay, so let's see how do we go from here to here. So condition 2 is easy because here we are saying that any vector of V can be expressed as a linear combination of EI. This means the span of EI is V. It's clear. And let's see why EIs are linearly independent. Okay, why do they? Why this set E1 into En is linearly independent? Correct. So for this, we will use this crucial thing that the expression, the linear combination summation alpha I ei, it's unique. So we will use this. So assume E1, E2, En is the basis of V, and E1 into En is not linearly independent. Okay, not linearly independent means linearly dependent. Correct. Okay, so what does this mean? This set is linearly dependent means there exists alpha 1, alpha, there exists scalar, so that at least one of them is non-zero. At least one of the alpha I is non-zero. So this means 0 contain from alpha 1 inverse plus alpha 2 plus alpha n. So if you see from this definition of basis, we have written instead of V, we are now taking 0. 0 has this expression, and here say alpha I is non-zero for some I. Okay, and this should be unique. Correct. This expression should be unique, but now we have another expression for 0, that is 0 dot E1. It will be 0. When we add something 0, 0, we will get 0, 0, and so when this, we will get 0. So we are getting two expressions for 0. Correct? The vector 0. So which, this is a contradiction. To the uniqueness of uniqueness of this expression. the linear combination. Correct. So we are getting a contradiction. This means our assumption was wrong. It must be linearly independent. And from similarly, you can go from this to above definition. Okay, let's see that also. Okay, let's see how do we from this definition to above definition. So now we are assuming that E1, E2, En is a basis. Now we are taking the second definition. So we are assuming this, okay. This means E1, E2, En is linearly independent and the span of E1 is V. The basis, that is the span of E1, E2, En is V, and E1, E2, En is linearly independent. Okay, from span we will get, so for any vector V in V, V equal to summation F, there exists alpha 1, alpha 2, alpha n in K, so that we can be written in this form. This comes from here. Since span of E1 to En is V. Okay, but in the first definition, there is another crucial thing. It says that this expression is unique. So how do we prove that this is unique? We will do this thing. So while putting uniqueness, we will do this. So we will take two, say, suppose there are two expressions. We have to show that alpha I equal to beta I. Okay. Now uniqueness. Suppose here exist two expressions. So summation alpha I I1 to n is equal to V, and say beta I EI I1 to n. So these two are equal. So this is this one alpha 1 E1 plus alpha 2 E2 alpha and En, same as beta 1 E1 and En. Okay. From here, what we get alpha 1 minus beta 1 E1 plus alpha n minus beta n En equal to 0. As we are taking this definition where basis means this set is linearly independent and span is V. So since EIs are linearly independent, since it's linearly independent, this implies these vectors are 0. Alpha 1 minus beta 1 equal to 0. So alpha n minus beta equal to 0. And this will give alpha I equal to beta I for all I runs from 1 to n. Yeah. So that's how we see the uniqueness. This completes the proof of equivalentness of these two definitions. Okay. Any doubt? Any question? I'll stop here. Any question? If not, please drop your attendance. Hello? Any doubt? Question, comment, anything? Okay, then bye. We will meet tomorrow.